we're not like missing anyone who shows up just a little bit late. But I will say, just an overview what I'm going to talk about today is a large class of 3D topological field theories. In fact, conjecturally, all fully extended 3D topological field theories, okay, aka the good ones. Well, okay, saying all is kind of, you have to choose a target, and we're choosing the target of C-linear monoidal categories. We're saying fully extended, we're saying oriented, and then that gives you this class of TFTs conjecturally. So it's called the TVBW model, or the Turaev Viro-Barratt Westbury model. Sometimes people just say Turaev Viro, but that's they only considered a special case of this. So TVBW is more correct attribution. So what we're going to do today is first talk a little bit about just generalities of state sums. So I picked this example, which is, I mean, I'm gonna have to say a lot of stuff, to define this, and there had better be a point, otherwise why am I putting you through all this? And the point is that there's a lot of different state sum models in topological field theories, and so this is a good example. This is possibly the best studied example. It's in dimension 3, which means it's a high enough dimension to be like, non-trivial and capture a lot of general features. And it's low enough that you can see things. So before I, dive right into the, okay, let's see be a spherical fusion category, here's what this means. I'm going to spend some time on the generalities of okay, well, what does a state sum mean? And why, sort of why you might expect this to capture a much more general class of things than the examples that we've discussed before. So once we have that, so the TVBW state sum takes it as input a spherical fusion category. So I got to say what that actually is, and then defining the model. Okay, I just realized I didn't include these part 4. We will probably not get to it anyways, but if we do, I can say something about why, is this expected to classify 3D topological field theories, and point you to the paper of Chris Douglas, Chris Shummerprees, and Noah Snyder, which does a large amount of good work to chopping away at this conjecture. Before I get started in earnest, are there any questions? Okay, as you know, please do not hesitate to ask questions in chat, by unmuting yourself, everything. So there's this common paradigm in math where you make a definition by introducing extra structure, and then checking that the definition is independent of that structure. So there's many things we do in Riemannian geometry where your first approach is let's introduce coordinates, and then check that what we just did is independent of coordinates. Or maybe in algebraic topology we say, aha, I pick a CW structure and then I do a thing, and then it turns out not to depend on that structure. So in low-dimensional topology, it's very common to make the structure combinatorial. So sometimes that means you pick a triangulation. Sometimes that means you pick like a knot diagram. Sometimes it means you pick a Hegard diagram of your thing. And you're taking this like wibbly wobbly topological structure, and you're you're sort of putting this like more discrete, more rigid combinatorial structure on it. And so a priori, you write down some random invariant of like a manifold of the triangulation, it's not going to tell you anything. So the goal is to say, okay, well, this doesn't depend on the triangulation. And another, again, this comes up all the time in low-dimensional topology, is you show that any two combinatorial structures on your same underlying topological object are related by a finite set of moves. I'll give some examples in just a sec. And these moves are local, so you can look at them only within a small disk. And so hopefully by combining, so you define your invariant, and then you say, okay, I check on move 1. If I make a move 1, the total invariant doesn't change, especially if your invariant is also local, meaning you can compute it somehow from like data near your move, such as a topological field theory, which ought to have locality because you can isolate a bordism containing that, and then the rest of the stuff is unchanged. So you check on move 1, you check on move 2, etc. You check on the final move, and then you've shown that what you have is a topological invariant and does not depend on the combinatorial structure. So again, I'm speaking in vague terms because this is a really common technique in low-dimensional topology. And we're doing 3D topology, so that is in fact low dimensional. So that the TVBW state sum is an instance of that. So one common example is knot invariance. So there are many invariants defined by choosing a knot diagram. So you take your knot, which really lives in S3, and you project it generically onto a plane. Well, I guess, yeah, maybe an S2. And you now have, you have this immersed, not immersed, you have this S1 sitting inside S2, and you keep track of, well, okay, when there's an intersection, does it go over, or which one goes over and which one goes under? And so there, different projections give you different knot diagrams for the same underlying knot. And as well as, it depends on the isotope, like the specific embedding inside R3, not just its isotopy class. So you have to check that if you define an invariant using a knot diagram, that it's invariant under Reidemeister moves. These Reidemeister moves are 3 different moves which relate equivalent knot diagrams and which generate all equivalences of knot diagrams. So R1, allows you to say, okay, this loop is folded over itself. Let me just straighten that out. R2 allows me to pull 2 strands across that aren't tied together. And R3 allows me to move, this third strand down below 2 more. Again, lots of knot invariants that are defined this way. So for example, a common favorite knot invariant is the Jones polynomial, and you can define it in this way, using a like saying what happens in, you define it in a different way, but then you check, okay, well, under R1, R2, and R3, how does it change? And the Jones polynomial is defined in a local enough way that this is fine. So another example, which is, knot invariants you may or may not have seen, but the Euler characteristic you've probably seen, where what you do is you choose a triangulation and you count the cells, and you want to check that the answer doesn't depend on the triangulation. You could do this locally. You can say, okay, well, what things can I do? I can further triangulate a manifold. I could join 2 things together into a bigger one. How does the Euler characteristic change? And the answer is it doesn't, because it actually depends on the manifold. So what we're going to do with the TVBW model is we're going to do this to define a topological field theory. We introduce a triangulation, or maybe something slightly more general, on our 2 manifolds and 3 manifolds. And using that data, we're going to define state spaces and maps on bordisms, hence also partition functions, and end up, and we're going to define invariant. We're not going to show, because the proofs are a little bit annoying and involved, but you can do. And again, there's this, I'll point you to the reference. You check that this, first of all, only depends on the underlying manifold, not the triangulation, by checking what are called Pachner moves, and then showing that it satisfies, disjoint union and gluing, so that it's actually a topological field theory. So this is a quite general approach. In fact, I think it's roughly conjectured that you should be able to do this to get all topological field theories for, say, oriented manifolds valued in something like reasonable. So like if this sentence is meaningful, you could care about TFTs valued in some like n category versus an infinity n category. And I think it's generally expected that state sum models should get you all the former if you're not doing something weird. So as an example, so typically you get something like an input data of a category with some additional structure. So hiding behind the scenes, if you've heard of the cobordism hypothesis, the category is what gets you a framed topological field theory, and the category is small enough that that works. And then the additional structure says, this doesn't depend on the framing, only on the underlying orientation. So today we're going to talk about what's called a spherical fusion category. And then we'll obtain a 3D oriented TFT called the TVBW model, which, and this is a very, very general class of 3D TFTs. You might also do, you could do a slightly more general, slightly different thing where you could say, I want a ribbon fusion category. And so this means that you get different kinds of string diagrams, and you end up with what's called the Crane-Yetter model, a 4D topological field theory. So here is a story. Crane and Yetter initially set out to define this nice state sum invariant of 4 manifolds. They knew that it was a topological field theory, but their point was just to get at 4 manifolds and to find something interesting. And they were hoping that, maybe this thing that we do can help define some, maybe it provides maybe it can help us detect exotic stuff, or, maybe it's just an interesting invariant, even if it's not helpful for exotic things. And then along with Lewis Kaufman, they showed that it is determined that for a subclass of things called modular tensor categories, so the ones that were sort of best understood and most interesting, the Crane-Yetter invariant, the partition function of the Crane-Yetter TFT, is determined by the Euler characteristic in the signature. Whoops. So this seems kind of bad until, and then Dennis Sullivan pointed out, you know, people have been looking for a combinatorial formula for the signature for a long time, and you've just told us one, so congratulations. So that's nice. You know, happy than sad than happy. The more modern point of view on this is that the Crane-Yetter model you can actually show is an invertible topological field theory for a modular tensor category. And so there are various ways of doing this. You can use like all sorts of category theory to say, well, what are the invertible objects in this category of two category of braided monoidal categories, and show that modular tensor categories are examples of that. Or more sort of straightforwardly, you can follow a line of reasoning that Chris Schomer-Priest gave, where you say, okay, so Chris has a theorem that to check that a TFT is invertible, in non-pathological situations, which include 3D and 4D oriented TFTs, you can just check on all Tora. Well, okay, there's one, but if you had like spin structures, you'd have to check on multiple ones. And so you compute the Crane-Yetter, the state space of the Crane-Yetter model on a torus, and you get that it's one-dimensional. And then using Chris's theorem, you automatically conclude that the Crane-Yetter model is invertible. And there's a third proof by Free Telemann. Unpublished work of Free Telemann. I think with Claudia Scheinbauer, they're finishing it up and publishing it, although I'm not 100% certain. And so they say, okay, well, let's extend this thing and then look at its values on spheres, and that's enough to imply invertibility. Anyways, okay, all that aside, once you know it's invertible, we classified invertible TFTs 2 days ago. And so you say, well, what are the homotopy groups of MTSO4? Or sorry, let me say that differently. What are the SKK Bordism groups? This is the way I said it on Tuesday. What are the SKK Bordism groups of oriented manifolds in degree 4? And you end up getting that it's determined by that, like, the SKK invariant is determined by the Euler characteristic. Or sorry, all SKK invariants in this dimension are determined by the Euler characteristic in the signature. So in some sense, the signature comes from P1, and the Euler characteristic is the additional thing that we got from the SKK, like by asking about SKK instead of just Bordism. Okay, sorry, that was a lot of digression, but there's there's plenty of more state sums. So one thing you could do is in dimension 2, things like Frobenius algebras give you TFTs. And so, for example, there's a state sum for 2D oriented TFTs, which replicates the thing that we already knew how to do a different way, but it's a good state sum. There's a different variant for spin. There's one for R spin. So in R spin, so a spin structure is sort of a lift from SON to its double cover of the frame bundle. In dimension 2, SO2 has lots of covers, not just a double cover. And so if you lift across the R-fold connected cover, that's called an R spin structure. So I'm trying to remember, this was someone's PhD thesis. What is their name? Damn it. If you search for R spin topological field theory, you'll come across this state sum model. I think it's Laurent Sekeli, maybe. And it's a cool thing. You get a nice Frobenius algebra-like classification. So highly recommend that paper. There's other state sums which are not fully defined as TFTs, but like, you know, they're gonna be. So Chris Douglas and David Reuter have a 4-dimensional state sum using the data of a fusion 2 category. So something slightly more general than what we did here. There's Aspen, Lake, and Walker have a 3D spin state sum. Kevin Walker has some sort of general arguments about, like, you should expect very general state sums with certain kinds of data. So the point is, sorry, to summarize all that, there's lots of state sum models. They're very general, and they all follow this kind of general recipe of pick some categorical data, you know, triangulate your manifold, and then use this data of the triangulation to, like, you know, maybe and the categorical data to define an invariant, and then, you know, check that it's independent of the triangulation. I said a lot of words, so let me pause for questions. All right, we're going to get into more concrete stuff in a sec. So what kinds of categories are? I mean, categories are very general, but the kinds of things that show up in state sum models are special, you know, much more special. So usually, especially in dimension 3, these things have enough structure that you can do things like make sense of simple objects. So a good example is the category of representations of a finite group or a compact Lie group. Well, finite group is better because those categories are small enough to do this. And so you can say, well, you can make sense of like when an object has a sub-object, and then okay, does it split off? And so you get these nice decompositions of objects into simple objects. And so in some sense, we're thinking of those as the generators of the category. And so you can color a triangulated manifold by saying for every edge, for every one simplex, we assign a simple object of the category. So maybe there's a representation on every, an irreducible representation on every edge. So the state sum model says, okay, pick a coloring and get out a number, which you can think of as the weight of the coloring. And then we're going to perform this weighted sum over all colorings. And that is how the state sum model is defined. And so you have to check how it behaves under change of triangulation. And I said those are called, the moves are called Pachner moves. So we'll see what those look like in a sec. So, okay, quick fact sheet about the TVBW model, Turaev Viro-Barratt Westbury. So the input data is a thing called a spherical fusion category. So this is a category status. So a lot of these constructions in like quantum algebra and 3D, they tend to say, okay, a modular tensor category is a thing which satisfies a blah, 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 blah list of axioms. A spherical fusion category is a C-linear monoidal category that is rigid, has blah, blah, blah. Okay, great. We're gonna march through those axioms, yes, but the point of this is, oh, and I should add a clarification, that you can make sense of, let's say I have a 3D quantum system, and maybe it's topological or gapped or something. It can have particles. And because space-time is three-dimensional and not four-dimensional, that restricts the ways in which particles can move around each other. And that actually gives us additional possibilities. So in dimension 4, particles are either bosons or fermions. And that has to do with the fact that, like, if I sort of move two particles around each other, then I can sort of unbraid that. So you can't get this, like, so somehow what that means is that you've got this additional symmetry structure, which prevents your category of particles from, that puts severe constraints on your category of particles. And so the only particle types are bosons or fermions. And so in these 3D quantum systems, particles in space are confined to a plane maybe. And that prevents you from, like, that means that you can move particles around each other, but that's not the isotopic to the identity. And so you get also, so like in these systems, which are sometimes hypothetical and sometimes studied in things called topological phases of matter, you get these particles. And so if you're studying it in the real world, it's not an actual particle because, you know, we only have bosons and fermions, but there are patterns of like localized excitations which behave like particles and which have these new kinds of behavior. And so they're called anyons, which is kind of funny. And so you can say, okay, let's say I have, like, you can try and build like anyons form a category. So, you know, maybe an anyon has a state space, and then you can smash them together, and that's some sort of tensor product. And then there's a braiding coming from how they move around each other. So, and then you could also, so a lot of these structures, like, you know, ribbon tensor category or whatever category, are saying, okay, well, let's say I consider categories of particles in this dimension. What kind of behavior can they have? And this is a reasonable thing to expect for topological field theory, because in these topological phases of matter, which are described by the behavior of their particles, at low energy, these things should be described by topological field theories. And so it's reasonable to say, okay, well, given the data that defines a topological phase of matter, maybe I should also expect that classifies topological field theories. So that's the kind of physics reasoning that is fast, high flying, and then turns out to be helpful and, like, conjecturally correct. As far as we can tell mathematically, this is right, which is really nice. So spherical fusion categories. It's also super anachronistic. Like that is not what actually happened in the order of things. The manifold invariance came first, and then the understanding in physics came later. But it's still, if you want to know why the heck should I care about spherical fusion categories, there's this take that they axiomatize this particle behavior is helpful. So there's this paper of Eric Rowell and Zhenghan Wang, which maybe provides, like, says better than I can what is actually going on. So I recommend their paper. So that's physics. So the actual story, like I said, Turaev and Viro first defined the state sum. I think I forget the name of their paper, but it has the word 6J symbols in it, where C is the category of modules for this thing. So first of all, UQSL2 is what's called a quantum group. It is a Lie groups. Compact Lie groups have nice categories of representations, but they're too big. So you can deform the representation category in a certain way, and then quotient out, and obtain what's called a modular tensor category, the input to something like Chern-Simons. Oh, well, in this case, this is exactly corresponding to Chern-Simons theory for SU2. And so there's different deformations parameterized by roots of unity Q. And the problem is these theories are not super well behaved, well, they're reasonably well behaved, but they have a thing called an anomaly. And so, okay, disclaimer, I think I'm reading the literature correctly. Taking the Drinfeld double gets rid of the anomaly, but produces a different theory. And so the Drinfeld double of this quantum group, okay, well, maybe I should say like it is a spherical fusion category, but I'm thinking of this as the category of representations of this guy. So if Q is 1, then this is the universal enveloping algebra, which is sort of the universal algebra you could build out of a Lie algebra, where bracket goes to commutator. So they studied this like one special case, and then Barratt and Westbury realized, oh, well, you can generalize this to all spherical fusion categories. So following that, Balsam and Kirilov. So yes, good call. So Saad pointed out something really important, which is that TFTs need to have these finiteness properties, like we used finite groups yesterday, and the category of modules of the category of representations of a compact Lie group in general has infinitely many irreps, simple objects, and for these quantum groups we only get finitely many, and that's really important in order to define an actual topological field. Yeah, thank you, Saad. So Ben Balsam and Sasha Kirilov. So Kirilov is at Stony Brook and Balsam was a student. So they turned this, they sort of took this and ran with it and made it into a once extended topological field theory and studied its relationship with, I mentioned there's this tight relationship with these 3D quantum systems. So specifically, given a spherical fusion category, there was already known a 3D quantum system called the Levin-Wen model, so a Hamiltonian model. And so these two studied the relationship with it, proved a relationship. So some of these papers are just Balsam, some are just Kirilov, a bunch of the two of them together. Good stuff. I recommend these papers. So this is how we got here. Any questions before I get into the details?
So you said that in 4D quantum systems, particles have to be bosons or fermions. Are
Yep.
you considering only point-like particles there, or?
Yeah.
Okay.
No, this is a good point, right? Because there's these string-like things, right, that have weirder behavior.
Yeah, I guess. I think so.
Oh, I mean, I don't know much about this. That's why I was asking you.
Okay, that was my vague impression. So thank you for confirming that.
Yeah, no, this is a good question. I mean, I guess, yeah, when I don't really know what a particle is, but I do sort of imagine it being localized. And so this is a great question, because if you want to study 4D topological field theories, you can't do this thing where you're like, aha, particles give you interesting information. So you have to ask about like, okay, well, what other stuff do I have? And so I think, honestly, it's something I'd like to know better, that you can look at like, these like non-local things. So like line operators or strings or whatever, and they have interesting categorical behavior. But yeah, no. Okay, cool. That's a cool question. I want to know more about this. Are there more questions? Okay, I'm going to press on. As always, feel free to interrupt me. So I'm going to march through this list of axioms. So first of all, we're going to start with a C-linear category. So C-linear means that the spaces, so the sets of morphisms between two objects, these have the structure of complex vector spaces, and composition is a linear map. So you've seen many examples of C-linear categories before, such as the category of complex vector spaces, the category of supervector spaces, the category of representations of a group. But we're going to consider more general things. So then we want a monoidal structure. So on Monday, we talked about symmetric monoidal categories, where there's a tensor product and a natural isomorphism V tensor W to W tensor V. So we're not going to ask for that symmetry. We're just going to say monoidal structure. So one good example of a non-symmetric monoidal category is vector bundles on a non-abelian group. So there's a convolution operation where you sort of like to take the tensor product, you say, okay, well, let's take the tensor product over, let's sum over all combinations G and H, whose product is X that we're looking at. So, okay, so maybe to do this right, we need a finite group. But because GH is not equal to HG, then like the tensor product is not symmetric. Anyways, we just want a monoidal structure. Symmetrical monoidal would push us up into higher dimensions in general. So with the structure of a monoidal structure on a C-linear category, and we're saying it's bilinear on morphisms, which is, again, the kind of thing that really you want to be true. You can define irreducible and indecomposable objects. So these two notions usually coincide in rep theory if you're doing like, if your life is good, but oftentimes it's not. So irreducible objects or simple objects cannot be split as direct sums in a non-trivial way. So maybe one of these is a zero object, that doesn't count. Indecomposable is a stronger notion, which said, or no, shoot. Crap, I always get this wrong. So if you're irreducible, then you are indecomposable. So indecomposable is a weaker notion, sorry. So what that says is your object cannot be written as an extension in a non-trivial way. So in vector spaces, you can always split short exact sequences. So irreducible and indecomposable coincide. Maschke's theorem says that if you're in characteristic 0, you can do this, the category of reps of a finite group or even a compact group for a generalization. Irreducible is the same as indecomposable. In positive characteristic, this is not always true. So the reps of Z mod N, sorry, the reps of Z mod P over a finite field of characteristic P this is not, like these two things do not coincide. And this is slightly annoying sometimes. But the point is we don't need any of, like all the structure we need is C-linear monoidal, and we can ask about this. So we're gonna say, those problems that I just said, throw them out. We only want semi-simple categories where irreducible and indecomposable coincide. So as I mentioned by, I just mentioned this example that Maschke's theorem says characteristic 0, the category representations of a finite group is good. But in general, in positive characteristic, it's a problem. So first we're going to say a fusion category. So a fusion category is it's a C-linear category. Hom spaces are complex vector spaces. We have a tensor product, and all objects are direct sums of simple objects. So extension split. Next, we're going to, so as Saad mentions, we want finitely many isomorphism classes of objects. And this just says it's not too big, so that we can like define a topological field. Two more axioms. One is that objects have duals. So on Monday, I told you about duality in the symmetric monoidal category. They're in a monoidal category, you have notions of left dual and right dual. And one of them is the S diagram and one of them is the Z diagram. And we're going to say, shoot, thank you, David. Good clarification. Yes, okay. So I said finitely many isomorphism classes of objects, and this is just wrong because like vector spaces, there's infinitely many. And we should say simple objects here. So yeah, so as David pointed out in chat, thank you very much. So, okay, so we're asking objects have both left and right duals, which again, so it's saying that you have the data for the S and the Z diagram. It's just that the left and right dual might not coincide. And finally, we're going to ask for the unit object to be simple. And this one is more of a niceness thing rather than we need this in order to actually do anything. Like you can define state sums for what are called multi-fusion categories. Is that right? I think. Okay. So, okay, great. Thank you. So once you have this list of axioms, you have a fusion category. And these are, already this is an interesting thing to study. And so the quantum algebraists, they go off to the races, and there's lots of interesting like classification theorems where they say, okay, if you know your fusion category looks like this, there's only so many kinds of things that you can have. And here's what they are. Or, if you know the growth rate of your fusion category, which is an invariant, then maybe you get some other like nice theorem about it must be reps of a group or something. So now we want additional structure. So behind the scenes, this is conjecturally saying, okay, a fusion category gives you a framed 3D theory, and then we want orientations. So in complex vector spaces, we have a natural isomorphism from the identity to the double dual. In a general fusion category, though, this is not true. You only have a canonical trivialization of the quadruple dual. So this is absolutely, I remember reading this and it's absolutely wild. Like why? So this was first proven by Radford for, I think, if I have my history right, this is entirely algebraic. Like, Radford just did this with without any like, not caring about TFT or whatever. It was just a thing. Maybe studying Hopf algebras, if I'm remembering correctly. And then Chris Douglas, Chris Chalmers, and Noah Snyder then showed that you can think of this in terms of topology. So there is a specific Bordism that they call the Radford Bordism, which implements this trivialization. In other words, given a fusion category, you have a frame 3D TFT, and oh yes, finite dimensional vector spaces. Thank you. Yeah, sorry to clarify that here I mean finite dimensional vector spaces. Yeah, great. So what Chris, and Noah did, or Chris Douglas, Schumer, Fries, Noah Snyder, they exhibited a Bordism. So a fusion category gives you a 3D framed TFT, and so there's a specific Bordism which implements that natural isomorphism for the quadruple dual. And so they describe it. I think there's even a picture in their paper. So first, what we're going to do is we're going to say, okay, a pivotal structure. So a pivotal structure gets us back to the double dual. And so that's nice. And a pivotal structure, a spherical structure is really, it's a pivotal structure in the spherical condition. So we can define notions of dimension. And there's, because we're only in a monoidal category, there's, and not necessarily symmetric, there's left and right. And so one thing we can do is we can define dimension. So if you remember in a symmetric monoidal category, what is this doing? This was the string diagram corresponding to the circle. And so we saw on Monday that the circle, Z of S1 cross M, is the trace of the identity on M. And so that's telling you the dimension. So these two things are analogous, and they're telling you the like sort of left and right dimensions. Sorry, I didn't say what psi is, but it is the chosen pivotal structure, the isomorphism from X to X double dual. So so spherical says, okay, we want these two things to be the same. And now you know what a spherical fusion category is. Any questions before I go start digging into the state sum? Okay. So oh yeah, question.
Is this different from the natural trace in that like the last map or has to do with a different pair than the first map?
Wait, like, this? I mean, in some sense, they're like left versus right.
Like this isn't the trace of an endomorphism. It's the trace. It's like the map goes from X to X double dual. It's like categorically different from what we usually do.
Right. Yeah. That's right.
It's interesting.
Mm-hmm. Yeah. More questions. Okay. So I'm just going to say some notation. So all this notation is borrowed from Boltzmann and Kirillov. So the first thing we're going to do is we're going to add brackets x1 through xn to mean Homs from 1 to x1 tensor xn. So so the pivotal structure implies that this is invariant under cyclic permutations. So I can move xn all the way back here. I'm not going to delve into the details. That's a lemma. And so when I say is invariant, what it really means is it provides a natural isomorphism between these functors as you switch the permutations. And that's going to be helpful for us later. I'm just going to let S of C denote the set of isomorphism classes of simple objects. So that's a finite set. And ooh, good question. Is this supposed to be an expectation value? So the notation is very suggestive that this is an expectation value. So part of the problem is that this is a vector space. So okay, sorry, to answer your question, the answer is I don't know. But there's this, so I mentioned there's these two things coincide, and so you get a dimension of an object. And I want to say that the dimension is going to behave in a way that might be non-intuitive. It is not necessarily a positive integer. I think it can, in general, it could be, quite arbitrary complex numbers. So for example, there's a simple example called the Fibonacci category. in which there's two particles, one of which has like this, I think it has this nice well-behaved integer dimension, and the other has the golden ratio, 1 plus √5/2 as its dimension. So that's kind of wacky. There are ways to intuit, okay, dimension is telling you something. Actually, David, catch me if this is blatantly wrong, but you can think of the dimension of a vector space as saying, as I tensor it to many copies of it together, how does the dimension of that thing grow, like the actual dimension? And I think something similar is happening here. Like, it's telling you about growth rates of when you tensor multiple copies of the Fibonacci enneagon together. But I'm not 100% sure. So if that's blatantly wrong.
This is true in the physics settings because everything in sight is unitary.
Okay.
Non-physics settings, like there's a MTC with 6 simple objects where one of the particles has, air quotes particles has dimension -1. So
and then there's a problem. Okay. Cool. Hey, thank you for weighing in.
Sorry, Aaron.
Yeah. What's up?
Could you give us an example? I missed it. You said the golden ratio. Was that an example of a dimension of a category, or?
So no. So there is a category. I haven't told you what it is.
Okay.
And it's one of the particles has the dimension, the golden ratio, which is kind of weird when you're used to. Yeah.
Okay.
Is dimension only defined for simple objects? I don't see why it should be, because you could, the dimension of a direct sum, you could just say it's the sum of the dimensions. Plus, I guess we defined it. I mean, we defined it not just on simples, so it should be defined everywhere.
Right. I guess I was just wondering if the left and the right only agree on simple objects.
So if they agree on simple objects, then I think you can factor.
I see.
You can factor these maps, I think.
Okay, thanks.
I'd have to think about that, but I believe that's true. Right. Okay. Good. Chadron asked about scaling dimensions. That's okay. I think that is often true, but then David pointed out that that's not always true, because you can produce something which has dimension -1, but even though it's non-unitary, or I guess it's non-unitary, so that's sort of not a weirder example. Do we always have? Okay. Oh, thank you, David. Yeah. So Saad asked, do we always have n1 equals c, and that is an axiom. Oh, right. So the fact that n1 is c, I can tell you why that is. So there's an analog of Schur's lemma for these things, and so and roughly that tells you that if you're simple if and only if your endomorphism space is one-dimensional, and so the unit is simple implies that n1 has to be isomorphic to the complex numbers. So okay, so finally, the global dimension is just this quantity. We take the L2 norm of all the dimensions, and so you have to choose a square root, and that's a thing that matters. This is some complex number, and we have to choose a square root, and so that choice is part of the data of the state sum. Before I go on, there have been a bunch of questions in chat. Have people gotten their questions answered to satisfaction, and are there more questions? Okay, I'm going to carry on. Please continue asking questions. I'm loving the fact that there's all these questions. So I'm not going to define precisely. So okay, you can do this with triangulations, but then it's kind of annoying. And so what Balsam and Kirillov figured out is that you could use a more general thing where you say, okay, well, I also want squares and pentagons and stuff. So they provide a precise notion of what they call as the Polytape decomposition. So it's a certain sort of CW complex or PL structure, I guess. And so we're going to say a combinatorial manifold is a manifold with a Polytape decomposition. So all combinatorial structures on the same underlying compact manifold are related by just a small number of local moves called Pachner moves. So there's 2 in dimension 2 and 3 in dimension 3, and that's what matters for us. And so if you have 2 different triangulations, you can just modify them locally to get one from one to the other. So here are the Pachner moves. First of all, you could remove a vertex, which only has 2 edges coming out of it. Second, you could remove an edge between 2 faces, and make this bigger face. So you can see here's why polytopes instead of triangles are very, very much more helpful, because none of these things are. If you do this with 2 triangles, you'll generally end up with like squares and stuff, or even decagons. And finally, And this one only matters in dimension 3, not in dimension 2. You can remove a face. So you can sort of, you've got these two cells in here, or 3 cells, sorry. And then you join them together into this bigger one. So those are the 3 Packner moves. So now I mentioned that we want to color the edges of a combinatorial manifold with simple objects. But we're going to do something slightly fancier, which is we're going to say that we assign to every oriented edge a simple object, such that orientation reversal means choose the dual object. So this way we don't have to worry about like canonically orienting the edges, but orientations are still still part of the data. Like the state sum still knows about orientations. So I'm going to let L denote a color, and so it's it's a function from oriented edges to simple objects.
Hey, Arun.
Yes.
Sorry, these Packner moves seem weird to me. So can you do the reverse? Like,
Yeah.
can you add an edge and stuff like that? Or
Yeah. Sorry. So these
Okay.
should be yes. But Balsam and Kirilov, I used their figures, and so they did one direction, and it should have been both. So maybe next year I'll go in MS Paint. I'll double the arrows.
Okay, thanks.
Yeah, good question. Are there more questions? Okay. So we're going to find this. We're going to build the state space, and we're going to do it as follows. First, we're going to define this thing H of an oriented 2-cell and a coloring. And we're just going to say, okay, we'll take HOMs from 1 to the value of the coloring on these edges. So crucially, we put the edges in cyclic order, and we use the orientations coming from the orientation on the boundary of F. But we have to choose a starting and ending point. And the fact that this up to natural isomorphism doesn't depend on that is important, because that way we get this vector space with this choice that we know how to map naturally between these two choices. So now let's say I have a closed oriented combinatorial 2 manifold. So first, we're going to sum over all 2 cells. Then we're going to sum over all colorings. So what we have, H of sigma, this is not yet the state space, but it's sort of maybe the pre-state space. Probably some of you are wondering about some intuition for like what this actually is, and I don't have any intuition for it really. It's other than it's like sort of an auxiliary thing we have, so that the actual state space is easier to define. So next, what we're going to do is we're going to find a vector associated to a 3-cell, which lives in the state space of the pre-state space of its boundary. So let's say F is an oriented 3-cell. Sorry, yeah, this should say oriented. We're going to define a vector, and given a coloring, we're going to find a vector Z in this state space for the coloring for the boundary. So first, we think of the boundary as S2, and S2 has a particular polytope decomposition pi, which just because it's a cell in a bunch of 2 cells in it. And now we're going to take the Poincare dual polytope decomposition. So just to clarify what I mean here, Poincaré's original proof of Poincare duality said, okay, triangulate your manifold. Now take the dual, not quite triangulation, but polytope structure, and then the numbers of cells correspond. So out, when you do this on cellular homology, out comes Poincare duality. So the labeling of pi gives you a labeling of pi dual. So specifically, we say that L dual of E dual is L of E when E is given the dual orientation. So E and E dual meet at a single point, and they're both edges. So I want to say if I'm heading along in the direction of the orientation on E, then E dual should go from right to left. And so otherwise, okay, if it goes the other way, then you just you flip it, which means taking the dual. So we now have a coloring of pi dual. So okay, so this is the part where I'm going to wave my hands the most, sorry. But for every 2-cell of pi, equivalently 0-cell of pi dual, we choose an element of the wait. Why did we choose phi C? That's weird. We shouldn't choose. Okay, so we're going to choose this phi sub C, which is a functional on HCl. right? So sort of given that we get, it's a way of evaluating. So you can define a string diagram by removing a point of S2. So you're now in R2, and then using the edges in pi dual. So these dual things as strings joining the objects phi c at the vertices. Okay, so we started with 2 cells, now we have 0 cells. And so you can evaluate this diagram by contracting an edge to evaluate a vector and a covector. So again, sorry that I don't have the pictures, which probably make this a little clearer. But again, check Balsam and Kirillov. And so a priori, this depends on the choice of point, and the spherical structure is exactly what guarantees that it doesn't matter how you remove this point. So people talk about, for example, the sweeping axiom, which says that you can think of this diagram as living on the sphere, and that the different ways of putting it on the plane are all equivalent when you evaluate.
Hey, Arun?
Yeah.
Sorry, I missed what pi was.
Pi is the polytope decomposition. So
Oh, okay.
on S2. So S2 is really now it's a polygon. Maybe it's this one. Maybe it's this one. And then you can take a dual.
Okay.
Oh, maybe it's this one. Anyways, that's almost all of the polyhedra I have within reaching distance of my desk. Are there more questions? So I figured out the answer to my question, which is this choice is auxiliary. What we're saying is that if you pick the choice and you got out a number by evaluating the string diagram, this procedure is a function from all of the choices to the complex numbers. So we have a functional from boundary of F with a coloring to dual to C. So evaluate string diagrams gives this functional. Therefore, it's an element of HFL double dual, which is equal to HFL, right? Because this is a vector space. And so this element, right? So we have an element of this, and that is what ZFL is. So again, we just have a 3-cell and we just have a coloring. So this is like auxiliary stuff. Shoot, I put a lot of stuff on the slide, sorry. So now, let's say the M is a closed oriented 3-manifold. So we're going to tensor over all 3 cells. And so what do we actually get? So we're tensoring the H of the boundary. And so what this is there's the stuff on the boundary, which only bounds 1 3-cell. So that's out there. And then everything else bounds 2 3-cells, because in polyhedra, you better bound, that's what polyhedra means, to prevent degeneration. And when it does so with opposite orientations. So we have HCl and HCl dual. So what we can do is we can get rid of these summands by applying the evaluation map, from a vector space to its dual. And therefore we only end up, so we go from this huge space to just H of the boundary. So what we're going to do is we're going to apply this to the vector where we tensor over all 3 cells. Right, so that lives in this thing, as we described how to end up in this for each 3-cell we ended up in H of delta or boundary of FL. And now we tensor product, we end up in the tensor product of these. And now we do this construction to get to H of boundary of M. And we're going to call that Z of ML. So we now have something which really looks like a TFT, sort of, where you say, okay, I have a 3-manifold with boundary. I get an element, that's aborted them from the empty set to the boundary. So I would like a map from C to the vector space in the boundary. So where does that send 1? It sends it to an element of the vector space of the boundary. So we're not there yet. There's still combinatorial structures and there's still colorings, but this is beginning to look like something. So we should sum this over all weighting. Weighting is synonym for coloring. I should have said coloring, sorry. So we perform this weighted sum, this formula, so first we have the total dimension D. Then we have V. V is accounting for the number of edges. So we say purely interior edges of M count as 1, and boundary edges count as 1/2. And V of E should be N of E, sorry about that, is that count. It says, okay, interior edge, you're equal to 1. N of E is 1/2 for boundary edges. And so again, you're gonna have to choose some square roots. And so we're assuming that you've chosen, not just a square root of the global dimension, but also of the individual dimensions. And that's part of the data of the sum. So this is now a ooh, okay, this Z should be an H. But this is now this is starting to look like the what you assign to a bordism. And if you're thinking of M as a bordism with multiple boundary components, you say, okay, well, this tensor, this dual, right? Like you can sort of bring the two boundaries over to the same side, and then that's equivalent to the state space of this tensor state space of this dual, which is identified with endomorphisms from here to here. And so that's how you define it on a bordism. But first, we need to finish up the state spaces. So let's consider the sigma cross the identity in and so this, as I mentioned, that is a bordism. So we're gonna bring the outgoing boundary around, and so now we have it as an element of I called this H last time. So this is H of sigma tensor H of sigma dual. This is H. And so we have a map, we have an endomorphism of H of sigma to itself. This was the sort of the big thing that I said was not the state space. And so it turns out this is a projection, and we're going to define the state space of sigma to be the kernel of this projection. And you're saying, hey, we had to triangulate the interval, but you check that it's independent of that choice. And then you say, okay, I define this thing, and it really lives in H of the boundary. And so we can project down to Z of the boundary. So to summarize, we defined a state space on closed oriented 2 manifolds, and then given a compact 3 manifold, we defined an element of the boundary, which you can use to obtain linear maps on bordisms. So this is the definition of the state sum, although it's not yet clear that it works. So I'll do this and then pause for questions. So we already have a vector space associated to a oh yeah, okay, wait. So I said this, that if you have an oriented bordism, then you bring the end around to the beginning, and you get an element of the dual, like beginning dual tensor end, which is canonically identified with Homs from the beginning to the end. And so it defines a map, a linear map from Z of the beginning to Z of the end, as you want from a TFT. And for a closed manifold, okay, so you have to check that Z of the empty set is C, but that is true vacuously, and so we really get a partition function. So this does actually feel like a topological field theory. Are there questions? Okay, so I want to mention that we have not proved the theorem. So first of all, there's monoidality. Does disjoint union map to tensor product? And this is true. And this actually isn't that hard. It's sort of because you can pick a triangulation, and there's sort of an obvious triangulation on the disjoint union of 2 combinatorial manifolds, and you'll get the tensor product. And again, this is sort of vacuous. But then importantly, is this just an invariant of manifolds of the triangulation? So you have to check on the 3 Packner moves. And again, I'll encourage you to read this in Balsam and Kirillov. Packner moves 1 and 3 are not so bad. I think number 2 is the hard one, where they spend the most time. Why does the cylinder act as the identity? This is the fun one. We sort of made it tautologically true. And then finally, why does gluing of bordisms correspond to composition? And there's sort of a geometric reason. You can think of you can sort of reason about, okay, well, like a coloring, and some data on the boundary that identifies like that they're the same. So this is so this is believable, but you still have to check it. So we're not going to worry about that. So I want to say some examples. So first of all, yesterday we talked about finite gauge theory, where you sum the trivial invertible theory over all principal G bundles. And so that gives us a 3D oriented TFT. And so we should hope that gives us a spherical fusion category. Because I promised that this thing should be a very general class of 3D TFT. So it better include some nice examples. So what you get here is the category of G-graded vector bundles. So you can think of that as, or vector bundles over G. So the modal structure is convolution. And so as I mentioned, this is generally not symmetric unless G is abelian. So the element in grading G is you take homogeneous elements in V and H, and then K, such that H times K is G, and then you sum that over all those pairs. So, okay, this turns out to be a fusion category. Because G is finite, there are finitely many simple objects. So the standard pivotal structure on vect gives us one on vect G, and turns out to be a spherical structure. And so, like I said, this is finite gauge theory, which you may have heard called untwisted Dijkgraaf Witten theory. This is the kind of thing that, like, if you'd like to chase, I didn't write any exercises for today's lecture, but this might be an interesting one to puzzle out. Like, well, can you prove this? Like, what is a coloring by one of these things, and what does this sum look like on a surface? But we can also we also allowed we also took states finite path integrals where we twisted by a cohomology class, and that gave us something called Dijkgraaf Witten theory. So here an interesting phenomenon happens, and this seems to be a general thing, which is the isomorphism class of Dijkgraaf Witten theory only depends on a cohomology class. But if you actually want a theory on the nose, you must choose a cocycle. And so this is, we saw this because of this fancy, like, okay, well, classify invertible field theories, Glacius, Matson, Tillman, Weiss, SKK invariance, Picard groupoids. But this was first seen by Fried and Quinn way back in 1992, where they just wrote down Dijkgraaf Witten theory on the nose, and they saw that you need a cocycle to define it, but cohomologous cocycles give isomorphic theories. So we're going to choose a cocycle. This n had better be a 3. Sorry about that. So if you've seen group cohomology, cool. If not, all you need to know is it is a map G cross G cross G to C star, which satisfies certain things. And part of the data of a monoidal category is the associator. That is, on a ring, association of multiplication is a condition. It's true or it isn't. When you categorify, it becomes data. So you need a map, a natural transformation from U tensor V tensor W to U tensor V tensor W. And so what we're going to say is we define that on these homogeneous elements and then use linearity to extend. So alpha is we're going to start with the standard associator coming from vect, and then we're going to multiply it by the scalar, G alpha of GHK. So for non-trivial cocycles, this can be quite interesting. So you have to check that the associator satisfies the pentagon identity, but this is true, like the cocycle condition is exactly what you need, which is kind of cool. And so you end up getting a spherical fusion category, and its TVBW model is Dijkgraaf Witten theory for that cohomology class. I'm almost done, but let me check for questions before I say a couple more examples.
Is alpha
yeah.
planning on n? Sorry, there are 3 copies of G here. Does that have anything to do with alpha being a?
This should also be 3.
Okay, cool.
Yeah, sorry about that. Yeah, right, because all this is in dimension 3. So if you're doing this in dimension 4 or something, then you would pick a 4 cocycle and you'd be twisting like some other kind of data in a monoidal 2 category or something. And then lower down, if you wanted to find Dijkgraaf Witten theory in dimension 2, okay, that should be some sort of Frobenius algebra. So you use a 2 cocycle to twist the multiplication, right? Take in 2 different things, and so you get G cross G instead of G cross G cross G. But yeah, right here, this is all 3-dimensional, sorry. So I'm going to say 2 more examples kind of quickly. I'm not going to go into detail. I'm just going to say these are families of things which are interesting examples of spherical fusion categories. So I mentioned that Turaev and Viro did this for quantum SL2. So what you can do is you can deform the universal enveloping algebra of a semi-simple Lie algebra by the quantum parameter Q and C star. And for Q a root of unity, it is possible to extract a spherical fusion category from the category of representations of this. So in general, there's infinitely many simple objects, but for Q root of unity, you can sort of kill a bunch of them and get out a spherical fusion, well, a modular tensor category and then a spherical fusion category. And this is closely related to Chern-Simon theory for the simply connected form of this group, and they're not the same, but they are related. I think this is a hard theorem of some people. So these give you lots of interesting examples of spherical fusion categories. So for example, the Fibonacci category I mentioned can be constructed in this way. And finally, there's some more examples. These are called Tambara-Yamagami TFTs. So we choose data of a finite abelian group, a square root of 1 over the size of A, and we choose a non-degenerate symmetric bilinear form into C star. So this data defines a spherical fusion category called a Tambara-Yamagami category, and hence also a TVBW theory. So in which the simple objects are elements of A and then this additional object. And so the product is, it's the usual multiplication on A, on the abelian group. And then, but M absorbs elements of A, and M times M is just the sum of all these objects of A. So it's not simple. And the unit is just the identity of the group. So morphisms are defined to satisfy Schur's lemma. So this category is defined very like skeletally. And so you say, okay, well, the HOMs are C if you're isomorphic and 0 if otherwise. And then the associator satisfies this formula for these particular triples, and then other things with the identity. So Tambara and Yamagami classified these things, and they're also interesting examples of 3D TFTs. So that's all I had to say today. Sorry for running a little over. Thanks for coming, and let me know if you have questions. Oh, also, I forgot to mention, because David Ben-Zvi's class is meeting today, office hours are going to be a bit later. I will post in Slack what the time is, probably right after this. I just have to check my calendar. So sorry about that. But yeah, questions.